So get started. So good afternoon, everyone. It is my great pleasure to be here today introducing Dr. Ethan Murphy as our guest speaker. So Dr. Murphy is a research assistant professor at Dartmouth Sayre School of Engineering and a key collaborator with our Neurology department. So he earned his PhD in mathematics from Colorado State University, where he focused on a sophisticated 2D approach to electrical impedance tomography, or EIT for short. And please pay attention, and the EIT is also a keyword in his presentation today. And after working in defense applications and completing postdoc training at Worcester Polytechnic Institute and the Rensselaer Polytechnic Institute, Dr. Murphy joined Sayre in 2014, collaborating with Professor Ryan Hotter. And his research primarily involves physics-based electrical modeling and imaging electrical properties using EIT, along with innovative computational techniques to enhance these methods for particular practical biomedical applications. And his previous projects include pulmonary and perfusion monitoring, bleed detection, imaging for breast and prostate cancer, and muscle property imaging. And today we're excited to learn more about Dr. Murphy's research in electrical impedance imaging and modeling for neural applications. So welcome, Dr. Murphy, and then please get started.
Thanks for the introduction. The title of my talk is Electrical Impedance Imaging. I'm going to say EIT about 1,000 times, and modeling for neurological applications. I'm working on a stroke and a tDCS project. I'm also going to take this opportunity to just talk about electrical impedance in clinical applications in general, and EIT in general, and a lot of the projects that we've done in Ryan Halter's lab over the last several years, some of which are kind of could be used for neurological applications and haven't yet. So, disclosure part, I guess I'm just on a couple of grants that are from commercial companies, Rytech Medical, Subware PI, and Medtronic, small grant. So, more to the introduction. So, why electrical impedance is relevant for clinical applications. I know it's probably not used clinically here, but we'd like to research it. And what is EIT? And then the recent work we've done, so I kind of said this already. And then the more in-depth neurological related projects, we've had a pilot study for EIT for stroke. And when we were doing that, we did this interesting thing with a portable iPhone electrode localization technique for high-density EEG caps. And then we're more recently investigating some tDCS, so transcranial direct current stimulation, where I'm doing a lot of modeling related to that. So electrical impedance tomography, E equals IR. So with cells, there's a general circuit model for it. It's a RC parallel circuit, but basically you have resistance of extracellular tissue. You have resistance for the intracellular tissue fluid. And then you have the cell membrane, which acts as a capacitor. And capacitors, they're really resistant at low frequency, and then have a low resistance at high frequency. And so what ends up happening is at low frequency, you're kind of probing the extracellular fluid, and at high frequency, you're probing sort of through everything else, or through everything together, sort of averaging it together. And so what's nice about that is at different frequencies, you're measuring different things. And why is that even important? Well, we have contrast in various things. So look at a histological slide of the 90 cancers tissue, very different types of cells. And when we do ex vivo studies, we see significant, generally like 50% for higher or lower values of cancer versus benign tissue. Additionally, there's lots of other contrasts that we find with electrical impedance. A big thing is lung monitoring. If your air fills your lungs, it becomes much more resistive, and air filling and emptying, you have a big contrast. Blood versus normal tissue ends up having a large contrast. Edema versus normal tissue. We looked at muscle versus unhealthy fatty muscle, which is pretty good contrast there. All right, so contrast exists, and then it'd be great. A lot of things are mathematically awesome and less awesome practically, but yeah, EIT tries to take that nice contrast and make images. And so the most basic picture of that is a circular domain, which no one is a circle in 2D, but that's okay. It's a circular domain. You have electrodes around the outside. You have some unknown conductivity inside. And so right now, just say it's a conductor and an insulator. We measure a whole bunch of data on the outside. So we have source and sink of current through different series of electrodes, measure all those sets, and then we try to make an image. Yeah, so that's the goal. Unfortunately, EIT is a soft field modality, so like it's not like X-ray where you shoot the X-rays right through stuff. In EIT, the current sort of diffuses through easily through the domain, and sort of a small conductivity change in some part of the domain will affect all the measurements. So it's a little bit of a tough inverse problem, but we model in physics. If we assume a known conductivity, we can predict the voltages on the boundary. We do some fancy math, do some linearization, calculate some derivative, solve some inverse problem. We get a pretty picture like this, where one can see that it's kind of blurry. But the yellow and blue kind of reflects the yellow and blue, the conductor and insulator. That is the start of this problem. So that's the gist of it. And if we can stick electrodes near where we think there might be some contrast, then we can try to do EIT. Yeah, and so from the engineering school, there has been some progress in bringing electrical impedance-based systems and EIT-based systems to the clinic. And this is just some examples. For skin cancer detection, there's a company called Neurological. They have an FDA-approved device. But like FDA-approved, probably still constrained to research mostly. There's a Starling device, Starling cheetah system that tries to get cardiac output monitoring in real time. There's also this clear edge breast cancer margin detection. And then another EIS system is the SciSpec-based one. It's not really FDA approved, but it's a device, a commercial company that we use for recording for many of our studies. And then on the EIT side, it's pretty mature in commercial companies making EIT for ventilation kind of applications. And it's kind of bigger in Europe, but for monitoring ventilation on ICU patients, we'll strap one belt around people's chest, and then in real time you'll see the air filling and emptying of lungs, and they can monitor like if the lungs are recruited, if they're recruiting properly, the front to back, side to side, and you can often match the positive expiratory peak pressure. Positive and expiratory pressure for tuning ventilation settings. Anyways, Timble, Draeger, Advanced Technologies, and again, SciSpec is a commercial company that we're using their systems. All right, so there's companies out there. We have contrast, we have EIT, and what do we do within our lab? So I just sort of categorized or separated into the different categories we have of things going on in our lab, and we have some things called absolute EIS or EIT, and so that's like we were going to measure the electrical properties of tissue, and we say, okay, benign versus cancerous tissue, do you see a difference? And that's sort of the absolute sense. And so some of the projects we have going on, an in vivo margin assessment probe, we have an R01 right now for prostate cancer, and an R21 going on for oral cancer. And this little picture to the right is about a 1 centimeter diameter where we just press that to the tissue of interest. Other things we've worked on an enhanced transrectal biopsy. So prostate cancer application where we add EIT electrodes to the needle. We've had pretty good results there. And then I'm going to talk more about EIT for improved stroke assessment, pilot study. So going on, we can also look at time series analysis of electrical impedance. And so then it's not absolute, but can we see stuff going on where we record the data quickly across time, and is there any sort of interesting patterns across time that give us good contrast? And so we've looked at that in terms of getting like a different method of doing PFTs. So maybe less, you don't have to blow it to a tube, and maybe you could just get it from regular breathing. We've also looked at lead detection, and so that was in a sort of an occult lead study where we're dropping electrodes around people and we're seeing if we can detect when there's bleeding before a vital sign, standard vital signs can figure that out. We've also done some porcine studies on traumatic brain injury. And then after that, so we have time series, we have absolute, and then we've also looked at multimodality EIT. So EIT is kind of blurry, but perhaps if we add it to ultrasound, and ultrasound is good, has high sensitivity, but could we possibly add some specificity by giving it some extra information from the EIT. That's what we've looked at for automated whole breast ultrasound and EIT for breast cancer, and for some handheld ultrasound and EIT for muscle assessment, both in some sarcopenia right now and some previous peripheral nerve disease applications. And then one more, we've also looked at something called cardiodynamic EIT or EIS, and so that's kind of like a multimodality thing where we're recording ECG or pulse ox signals, we record EIS really fast, and we sort of look at patterns between the two and try to tweeze out some interesting contrast. So, in a nutshell, this is, 70% of what I've been doing for the last 10 years, for better or worse. So, anyways, and then as I put that together, I kind of wanted to give like a top-level view of some of the strengths and weaknesses of EIT applications. And I really like these spider diagrams. But looking at it in terms of, well, how good is the sensitivity? How good is the posedness? Is it well posed, poorly posed? Is it robust to noise, small modeling errors? What's the depth of sensitivity? And how specific is the information? And so I'm sort of just not meaning like clinical sensitivity and specificity. I mean, conceptually, do we think we have sensitivity to measure the contrast in question? And then, if we measure this contrast, would we get confused by other things? So, kind of sensitivity and specificity, but kind of on that conceptual level. And so, our most standard EIT application, time difference EIT for lung monitoring, kind of floats around these kind of points on these axes. So we have good high sensitivity. It's pretty well posed. We're pretty robust to modeling errors because it's a time differencing thing. And we have good depth of sensitivity and good depth sensitivity because we're just looking at air filling the lungs. And specificity is all right for this application. And so we've gone on to that EIT for pulmonary function assessment. And it's kind of similar to the EIT for lung imaging, except maybe a little bit better in the posedness and the robustness to noise, because we actually have been finding we don't actually solve the inverse problem, we just look at average impedance across time. So we're a little bit better in those areas. And then for the bleed detection, it's pretty similar to the PFT approach, but we're trying to see contrast in blood, which is much smaller. So it's kind of a harder problem in one sense, smaller contrast, but better stuff. And then to make this a little bit more practical, so EIS for PFT assessment, this is what we're looking at when we collect the data. So this curve right here is our average impedance versus time. And if anybody's had a PFT and look at the traces of lung volume, it really mirrors it very closely. This is what the PFT text will be looking at, almost the same thing. And so right here, a person's breathing tidal breathing, so normal breathing. They take a really big breath, part of the PFT test, and then they blow it out for a really long time. Well, like 6 to 10 seconds, and then take a big breath in afterwards. So we recorded that data EIT-wise, we recorded the actual PFTs, and we end up getting nice correlations. And this is from a recent study we just finished, 32 ALS patients and 32 healthy controls. So we're pretty happy with that, and not to stay on this for too long, but potential surrogate for PFT, possible at-home monitoring, a lot of possible different applications. And then we've also looked at it as, can we just record regular tidal breathing and get similar correlations? And it seems like right now the answer is yes, so that seems like it has some nice promise there. So for bleed detection, I think this is nice to study, consider, well, I mean, nice to bring up because of the neurological applications. But for bleed detection, we did an interesting lower body negative pressure test, which is kind of far out. We stick this sort of, dress thing on the lower body of people, reduce the pressure there, and sort of the blood sort of goes into your legs and eventually pass out. But it's a nice controlled setting to test for bleeds. And so, besides torturing people, in an IRB approved study, what we're interested with is seeing can we see a change with the electrical impedance before the vital signs see a change? And so these box and whisker plots are showing what happens at baseline versus a small change in the lower body pressure, which is a small bleed, followed by a little bit more change, so more and more bleed. And so what we're seeing is significant differences with heart rate here at our second level of bleed. And when we compare that to the EIT, we're seeing sort of the change almost immediately. And also the difference between these two sets of distributions are better separated. And we're getting some really nice ROC curves in this really nice controlled setting, being able to detect bleeds really fast before standard vital signs. Yeah, I can talk more on that, but yeah. So a couple more conceptual ones. I love these more than potentially the audience does. But strengths and weaknesses for a couple other applications. Our surgical margin probe. We have like high sensitivity. We're actually touching the probe to the tissue that we want to say, is this cancer or not? It's pretty well posed because we don't have to try to aim to get too deep. It's also robust to small errors. Again, it's kind of a shallow problem. And then the biggest shortcoming is 1 centimeter wide sensor really can't go too deep. It's just a few millimeters. So that's one example. And then when we switched over to our sort of treat setup, so this is again the enhanced prostate biopsy. We're actually sticking the electrodes into the prostate, so we have great depth of sensitivity. But then there's a small factor that we have to fuse stuff, we have to track stuff, we have to solve this really complicated inverse problem. So we get knocked down a little bit in the robustness and the well-posedness. And also we're trying to image the entire prostate, so the sensitivity is a little bit lower. Yeah, so less on the treat stuff, but a little bit more on our surgical margin probe, a very recent study. We've analyzed 19 subjects right now with oral squamous cell carcinoma, as you can see. Oral squamous cell carcinoma. So an ongoing study where with our clinicians we're touching the probe during right before they have a cancer removed in their mouth to the benign and the tumor side, or to the tumor and then the opposite side. And so our bar and whisker plots using an interquartile range is showing really nice separation between the healthy and cancerous tissue. And we're getting pretty good ROCs for that. So it's again, another promising application of EIS. And so our AUC is at 0.88, accuracy is at 87%. And, okay, now finally getting to my more neurological applications. And with a recent Hitchcock Foundation pilot grant, we looked into stroke imaging with this combined, I have a typo there, high definition EEG plus PIT. And so you'll notice that things sort of shrunk down towards the center there. We have an unfortunate issue with the skull, so that really cuts down our sensitivity to things happening within it. The posedness of the problem is sort of hampered by having less sensitivity. There's going to be a lot of robust, a lot of noise to sort of the error chain of all the modeling that we have to do. And then similarly, the depth of sensitivity is kind of lower because we have to get through the skull. And I would say I just drew this big because it's to be determined. This other project that we did, I'm not going to really talk much on that, but traumatic brain injury. We actually stuck an electrode onto, I think, either the ICP intracranial pressure sensor. And so we had measurements within the skull, and then all of a sudden it's a great problem, but there's only certain sort of scenarios where you have things going into the skull. But sensitivity is much higher, it's a much more well-posed problem, not doing nearly as sort of a fancy analysis, so it's more robust to errors. And then we're trying to start up a recently funded different project for assessing strokes. We're calling it anatomical windows, and our novelty there is we're trying to stick electrodes on places where there's no skull. So I guess I talk about them. So we can stick them right on basically the eyeballs, right around there, the base of the skull, and we're playing around with the soft palate electrodes. So just trying to get different pathways to get increased signal. So high level, that's the kind of stuff we're looking at. EIT and EIS-wise in clinical applications. And then I wanted to go, straight into my the stroke study we've been doing. So I have a slide on the clinical need and problem of it, and I'm always embarrassed talking in front of clinicians that might know this 10 times better than me. So stroke is a serious problem. In these references, 5th leading cause of death in the U.S., leading cause of disability with more than half of the patients over 65 with mobility loss. 2 primary types of stroke, and I know it gets more complicated than this, but ischemic, blood clot or blockage, and hemorrhagic bleed. So just on a simple engineering level, I can understand that. And so for EIS, PIT to have utility, it has to be sensitive to both blood versus normal tissue and ischemic tissue versus normal tissue. So there's been prior studies on that. And then we were kind of ambitiously looking at a couple applications of EIT for stroke. And the first one is, can we help out with this golden hour? Can we help out with getting better or getting same information faster that currently is being done? And so, like right now, my understanding is as long as you get someone to the hospital as quickly as possible, you can give them a non-contrast CT, and you can definitively distinguish between stroke types, and then get them onto treatment really quickly. And so the question is, perhaps, it's a big perhaps, could EIS or EIT help in those settings? And then maybe more reasonably, could EIT help out in this maybe secondary, less intense problem, but very important, the continued monitoring that needs to be done after a stroke patient has been brought to the hospital, has had an intervention, and then has to be sort of stay in the hospital for up to towards a week, where they could have some secondary stroke progression in that time, and sort of constant monitoring would be helpful for that, as care is often overburdened. So long-term monitoring, real-time monitoring with EIS or EIT would be a possible solution. So whenever I talk about applications like this, I'm not the first person to look into this. I wanted to sort of emphasize that. We have a colleague over in London, Dr. David Holder. He's been working on this for many years in addition to other projects. He's helped establish the contrast of ischemic brain tissue to normal brain tissue. This is from one result from one particular rat model. He's published many studies, pushed a lot of the modeling and algorithmic approaches. I just listed a few references there to say that it's been looked at. And so where do we come in with this? Because this person's done a lot of work in it. What are we going to add to it? We had some interesting results with some incorporating soft primers, incorporating structural information from other modalities into EIT. So we're really excited. We also had some really preliminary EEG application. And so this seemed to make a lot of sense. So this is sort of the picture of what we're looking at, the gelatin head. So the team was myself, Ryan Halter, Alicia Everett, graduated PhD, and Haley Richards, a master's student, along with our DHFC team of James Song, Eric Polars, Dr. Tim Lukowitz, and Diana Rojas Soto. So we collected, after doing a whole bunch of engineering stuff, we collected on 7 acute stroke patients after being stabilized around the 2-day period. We developed a bunch of computational framework to tackle the problem and try to validate it. And so here's the framework for what we did. So in the clinical workflow is the top row. So we have a stroke event, they arrive at the hospital, can't change that. So somewhere in there they'll have their CT, they'll have their diagnosis shortly after that, some intervention. And we've been using the MRI as sort of a building block of our model, and they get that somewhere in there. And so after they've been stabilized, the clinicians say, okay, you can record your data, everything's okay for that. And that's during this big blue window of their observation for the discharge. So our study data collection, we placed a cap, we collected EEG, and we did these iPhone scans for some reason to be put later, and then recorded all of our EIT data. And so after we got that, we had this barrier problem with data processing. So these iPhone processing steps, and then we had 2 different ways of sort of going through getting all this data into an image of EIT. And one was using a generic mesh that was already there, and then sort of morphing it to the particular person. And then the other way was taking an MRI, making a mesh, registering all the information to it, and then making the image, overlaying with the MRI, and seeing how good you're doing. So of course, there's with anything. This is sort of my first real neurology problem. So we initially started, we realized we had lots of problems to solve, big engineering steps. And then after we thought we were good, we realized that there's this first obstacle that we need to know where the electrodes are in the person's head. And our standard approach to doing that, Yin-Shin had, was the patient would just have to sit within this photogrammetry setup in the EEG lab. And immediately we're like, well, the stroke patients can't just get out of bed and sit there. So we had to develop a portable technique to get the electrode localization information so we could get that into a model registered to the patient's head. So that was a big step. And then after that, we worked on the finite element, which is how to get physics modeling, how to get that from the MRI and the imaging scan. So our engineering step, a lot of things in engineering are very basic. We're like, well, you just have to plug that thing into that thing, and we're all good to go. So we have our EIT system, 20 channels. We have a 256 pin high-density EEG plug that connects to this cap. And so we had to look up specs, do 3D printing parts, and then do a lot of manual soldering to connect a whole bunch of plug options into the back end, so we could connect one system to the other. And then, that's probably isn't too interesting, but a whole sort of pseudo-optimization problem of, well, what kind of electrodes should we measure from? We can only measure from 20 at a time. So this diagram is trying to show how we select. We're putting on the plugs on the back end to get reasonable spots, and basically we want to make sure we're generally driving currents deep within the head, so we have good contrast, or we have sensitivity to the contrast. So after we did that, we did some fun gelatin head experiments to get a proof of concept. Are we able to map everything correctly and at least get some basic imaging to work? These inclusion position errors are relatively high, but this is kind of a quick and dirty analysis. But we consider this a positive thing. So over here we have our gelatin head flipped over, filled with saline. We stick balls in it. And we tracked everything with our EM tracker for validation. All right, so we're like, okay, we're good to go. And they're like, oh crap, we need to go get these electrode locations. And so we tried several different techniques, and we settled on iPhone scans. And we required taking sub-scans around the patient's head. We did 5 sub-scans. And that's great, they look pretty, but then you actually had to get the electrodes labeled on them, which was a little bit of a laborious process. And then we'd have some automatic converting algorithms, so we get some pictures that look like this. And this is from a recently published paper. And so in the paper, we evaluated on 8 subjects from 3 different breeders that independently did the processing. And qualitatively, I think hopefully everyone can see that they all look like heads. And then very subtly, there are tiny little red dots on each of the electrodes, and that's because we've labeled them and did a fair amount of manual clicking during the fusion process. So, some processing, we quickly record scans of the patient's heads, and then eventually get a nice, fairly accurate locations around the 3 millimeter range. All right, okay, good. Now we just have the MRIs, and our anticipated plan we'll take these MRIs and we'll just make finite element meshes and everything will be great. And from Yinchen's perspective, he knew the process, and it's just like, okay, we just need a 1 by 1 by 1 millimeter T1 scan of the full head. And unfortunately, clinically, that's not of interest. It's not like important to get that specific kind of scan for standard of care to assess how they're doing with their stroke. So if we had our perfect scan, we could call this automatic segmentation tool. It takes a long time, 6 to 12 hours. We could use some other brain science software called Brainstorm, register anatomical features, bring the HT, EEG locations into it, generate some surfaces, call up some meshing, finite element meshing software, make some pretty pictures, and then have some cool finite element meshes so we can do all our nice modeling in first one. And so what actually happened, the scans were not ideal because they did standard of care, and that's very important. And so we just had to take whatever we could find and see what we could get. And so we have what ended up being best for us was these axial SWI scans, and we did have one subject that happened to have a T1 scan that was almost or sort of our ideal. We had a whole bunch of Uji attempts to make it work. We used some brain science software that almost worked, and then we found an updated one that's designed for tDCS applications that was able to, with sort of minimal steps, to make these very nice images. And so it's a sort of automatic segmentation. We get a full finite element mesh, and it's separating out the white, gray, CSF, the skull between spongy and compact layers, and also eyes, blood, and some muscle. So, great solution by a group. I'm going to forget the name. But the Paralab in a New York City university that made the synapse. All right, so we have all our tools created, and then let's look a little bit at the data. So the patient information, we had a wide range of NIH stroke scores, so from 0 up to 20. The first 4 subjects had ischemic strokes, and the last one a hemorrhagic one. And the when we could collect the data, it seemed to settle around the 2-day mark. And so we're after, obviously, stabilization and intervention. So it's kind of like we're not exactly measuring an ischemic stroke, we're measuring what happens after the ischemic stroke was mostly solved. So potentially a fair bit of edema, and, well, it's kind of hard to get entirely. And similarly with the hemorrhage, obviously the hemorrhage was stopped by that time. So we're getting sort of after visuals. And these are the meshes that we're able to make along with the iPhone scans from the subjects. And you can see just funny little things of they don't need to get the top of the head, so that was cropped out of the imaging, and so we can't reconstruct that in the mesh. But pretty successful there. And then I probably had so much front matter because the EIT results were not amazing in this application, in this first pilot data. So these are the type of results we will get on some applications in EIT. I've circled in, I don't know how well the red is showing up there, but I've circled in red the regions where the stroke lesion is on particular patients. And we've tried some absolute EIT and frequency differencing EIT. We have a few other tools or examples we want to go through. Reconstruction out of which we want to go through. But in some sense, it's not like this totally doesn't work, but it's not definitely, this totally does work at this point. So we're seeing some contrast, a 10% sort of increase in the conductivity for 3 out of the 5 subjects. And that's interesting. It's only somewhat promising because the subject 3 and 4, 4 had the noisiest data by far, and subject 3 had a stroke score of 0 and a very deep stroke. So potentially these are positive results. If I were to block those out, things would correlate very well, but I can't do that. So somewhat positive results. There's a bit more work to be doing this. And I think there's a lot of lessons learned, and we built up some nice computational infrastructure as we went ahead on this. And again, we have a new R21 where we're analyzing these anatomical windows, and we're going more towards impedance across time. So the time series and the cardiodynamic stuff, partly because the absolute EIT is a hard problem that doesn't always work. All right, so okay on time. So the rest of my talk, talk's doing okay, dives into this other project that I've been recently getting interested in, and it's about transcranial direct current stimulation. And so very different from our lab's usual work, where we're looking for cancer, detecting strokes, mostly detecting cancer. And it's sort of collaborating with Tor Wager over in the brain science department over at Dartmouth College, but definitely has some future potential clinical applications. And so I've been doing similar modeling, making all sorts of finite element meshes, and doing all sorts of simulations. So I don't know how many people in the room are familiar with tDCS, and don't think it's used. I don't know if anyone's doing that research-wise at PhDs. But yeah, it's a non-invasive neural modulation technique, and it's been studied for a slew of conditions: neuropathic pain, fibromyalgia, migraine, anxiety, PTSD. You just, almost like if you name it, it's been studied on it. And a fair amount of positive results, and then some questionable results, and there's a lot of modeling and optimization techniques that have gone into it, seemingly to try to better understand the physics of what's going on and sort of better apply the electrodes and current to sort of better understand science. And so that's what I've been trying to help out with a little bit. So a weak direct current is delivered to a specific cortical area. And when I say weak direct current, it's like on the order of like a few milliamps. On the DC level, so the subject would feel tingling, but it doesn't like actually shock the person or activate, like directly activate neurons. And so the theory is it induces subthreshold modulation of neuronal resting membranes. So it's like in certain areas you change that a little bit, and the neurons are more likely to fire. And sort of some animal stimulation and a different kind of just negative current will have an inhibitory effect, sort of less likely to fire up. And so based on just that simple understanding, brain science people are like, okay, so we want this region to be more active. We'll apply this one. We want this region to be less active. We'll apply the catalyst. And if it works exactly like that, that'd be great. Like EIT, you get blurry images. When you apply electrodes to the surface of the scalp, it sort of diffuses and blurs out in other areas. So a problem is like we want the current density to go in a particular direction and not go anywhere else. And so that's part of the challenges with making this work effective. This is just a simplified picture of what's going on with a ginormous pyramidal neuron. But if if you have current flowing from the anode down, sort of like along its the neuron shape, then by this theory you should have sort of the best effect. Of course, like there's the whole cortical folding, and so you might be interested in stimulating a region that's not parallel to the scalp, and then things have to be sort of handled more carefully. So that's some of the modeling issues. So we did some initial exploration of this, did some optimization, and presented at the OHBM's Organization of Human Brain Mapping last summer. And after getting more into it, we've been doing some montage and subject variability studies on 41 subjects' scans that they have. So I just have a whole bunch of models based on real people. And it's using the T1 and DTI scans. And we're focused on the DLPFCs. And it includes anisotropic connectivity models and various electrode sizes, applied current application montages. So we're just sort of building up our understanding of tDCS at this point. And what we're doing with the models now I get my ideal scans, so I can do my ideal computational pathway, but we also get our DTI scans, and we can make some nice anisotropic modeling based on those, where we sort of take the white gray matter and we can get the directions of how current should flow. Brain science folks have this cognitive CAN lab GitHub repository where we can look at any brain region of interest. We just have to register it to our models, and then we get nice pictures of particular electrode montages, electrode setups, and our sort of our brain regions of interest. And so that's kind of models and things we're looking at. So I think I'll go through this slide and try to wrap things up. So DLPFC, I don't know enough about the brain science aspect of it, but I believe it's on regulation. This is emotional regulation, I believe. But anyways, it's an interesting site to stimulate, and they have nice standard ones where you just slap on a huge electrode right on the GLPFC, and then just say throw a huge electrode away from it. So that's like sort of the standard approach. And then the more modern ways, you should put the small electrode to increase current density over the region of interest. And then a newer approach is using, they call it high definition tDCS, but using this 4-ring plus 1/7 approach. And so we know that's what people do. So with the modeling, we can sort of look at, we can try to ask some questions, answer some questions from the models. What is the actual difference between the small and large stimulation electrodes? The effect of F3. So they often place these electrodes based on EEG locations, but there can be like some slight variability of where the EEG location is and the actual brain region of interest is per subject. So we can, with our model, we can place it directly over the region of interest. And then we can look at how good is this actual HD tDC that some groups have been pushing. And so with we're looking at different metrics on it. These two are called the average directional and the focality. And so both of these, if they're bigger, the better. And so just to quickly go through it, this is the kind of differences you have with smaller electrodes versus larger ones. The blue region here being the smaller one. The focality is about the same. And then precise placement is actually a really significant change. And that's really not often done. Only a couple of groups seem to do this with tDCS. so it's harder for admin uses. And the real cool part about the high definition tDCS is it really cuts down on locality, which is, are we just affecting the area of interest and not affecting other areas? And then precision with that one, precision placement of the electrode seems to be very important. All right, and then of course I can endless slides, other stuff. All right, and then with our brain science collaborators, they've already done some human subject testing. They've done some nice paper comparing tDCS with social induced expectation changes, so it's like the bias. Had some nice results. And going forward, we're really interested in applying these fMRI-based pain signatures to the tDCS. That's a specialty of a Tor Wager's lab over at Dartmouth. So they have these really precise fMRI-based parts of, well, this is like where the pain lights up, and this is the yellow is pain lights up, blue is anti-correlated to it. And so the hypothesis is if we stimulate these regions specifically with like a multi-electrode montage, could we have really improved effects on this? And so that's a long-term goal there. But 2 minutes left. My concluding remarks. I've kept everyone awake and excited. I hope I've showed that there's some pretty good potential in EIS, and I would love to be able to convince you that EIT is great, but the EIS and time differencing stuff seems to be definitely more possibly practical in clinical and neurological applications. Pushing it to be really clinically useful is obviously a remaining challenge. And tying the right EIS or EIT technique to the right application is something we really strive for. We don't want to just be solving nice math problems. And there's future work we want to be doing because we're really hoping to start some intracranial SEEG applications soon, some modeling of activation regions. At some point in the future, we'd definitely be interested in pushing the tDCS work to not just testing on healthy college students, but to move more into actual clinical applications where persons are experiencing, for instance, chronic pain, and you want to see how it actually works with those programs. So a lot of people helped out with a lot of these projects. Yes.
Would you be willing to go back to the slide that had the 3 columns and the 2 blocked out?
Yeah, sure.
I'm just wondering what you're thinking, because the 3 that weren't blocked out were so perfect, and then the 2, that you did block out were less perfect. So I'm wondering if you have a hypothesis for why.
So the 3 that I did block out were nice. So why 3 and 4 aren't really going where it's involved? Well, I didn't show how noisy the data of subject 4 was, but it was like an order of magnitude noisier than the rest of them. And one of the issues with that person is they had a nice set of hair. Our old subjects, most of them were fairly bald, so it's super annoying. But electrode contact is just a really annoying stumbling block with getting this to work well. So that could be one of the reasons. Subject 3 really had a small stroke and a very deep stroke. So it's a real challenge. They said, okay, we'll recruit the person, but it seems like if we could image that, then this would be amazing technology. I wish the images were just sort of like fine if we don't see anything, but it still seems. Yeah.
Nice talk, even though I only got the end of it. Can you explain a little bit what is your plan with the SEEG?
I'm not super great at thinking on my feet, but I have a pretty proposal on it. By diving into the literature, there does seem to be some contrast in terms of like epilepsy lesions, and then so it seems like there's potentially some contrast, and I kind of wanted to throw all our tools at it. So like looking at time series EIS, EIT, relating it to cardiodynamic stuff. So there does seem to be, I think there's some good. I wish I prepared this answer. But there does seem to be potential contrast with cardiodynamic EIS, with absolute electrical properties around the epilepsy region and versus not. And a lot of it's not tested. So based on some literature stuff, we think there might be contrast. We're measuring right on the region of interest. And so potentially we could add more information than is just given by the EEG. Potentially we add a slightly larger volume of sensitivity than like each of the EEG contacts has by sort of getting the impedance between sets.
Okay, thank you.
Yep.
Thank you for a fascinating talk. Regarding the first part of your talk, one of the holy grails of stroke research has been to try and figure out which patients are going to deteriorate. And do you think you might use your techniques to obtain a series of images and based on the changes predict and tell us who is going to deteriorate? And if I may make one other comment, which is that this issue was looked at with much cruder techniques 40 years ago, and unfortunately the conclusion was that the clinical examination looking at them deteriorate predated the changes seen on EEG. So it wasn't that the EEG was not giving us any useful information. But with your much more advanced techniques, do you think you could do a series of measurements that would tell us who's going to get worse?
I would love to say that you could potentially do that. That was kind of the ambition of the R21 starting up. So it's more focused on monitoring after the acute phase has been over. So I think there's definitely potential, and that's something we're looking into. I think we're kind of struggling on how long we can actually monitor patients in sort of a R21 fashion, because we can't just monitor for days, I don't think.
I don't see why not.
Well, it's just the IRB setting up a study and can we hook them into I don't know if we'll have a nice portable system ready that will allow them to. But we're looking into that, and yeah.
And then one further question regarding the second part of your talk. We've been interested in the epilepsy literature. There is now a small body of literature looking at direct current stimulation, claiming to show reductions in seizure frequency based on direct current stimulation. That might be a potential project one could get involved with, trying to tune the parameters of stimulation, because there probably is something there. What do you think?
Yeah, it's kind of very much discussed with seizures. Does it or does it not do something? So it's
I'm still trying to wrap my head around the tDCS stuff. You read some stuff that sounds a little hokey.
Yeah.
And I wish I could just use my tools and just definitively know something. But I can only model.
But I have to honestly say, so this field of like tCS and stuff, there's so much stuff out there where there's like a bunch of 10 patients and they gave them tDCS and they do better.
Right.
And what does it mean? It means nothing. I think the real thing is really to measure things, find good biomarkers to measure what does this really do and what does this not do. So I think you're totally on the right track there, yeah.
Yeah, I've read some discouraging efficacy of tDCS figures where they did a meta-analysis of many, many things, and they're like, it could possibly be working these two things, and it doesn't work, and this half dozen things. It's a muddy, muddled middle.
Okay, thank you.
Yeah, thanks.
Thank you.